And thanks for coming. Do we have the video and the sound? Is that all set up? Yes? All right, wonderful. All right, I'm really excited to be here today and have the first lecture on CS224D. We'll start with a couple of simple logistics and then really give you one of the most important ideas and high-level thoughts of deep learning for natural language processing through a series of natural language processing examples. And you see actually the output of a neural network and how it essentially classifies the sentiment. So for instance, the first 15 minutes where dry is negative, that's a negative phrase, and you see basically dry being negative and so on. But by the end, I really enjoyed the lecture, so hopefully this will be true for you as well, just like it was for this neural net. So maybe some of the most basic course logistics. Also, if you have any questions for any of the lectures, this one or any of the future ones, feel free to just raise your hand and ask the question. So my name is Richard. I actually got a Stanford PhD 2 years ago and then founded a small AI startup called MetaMind. And then we have a couple of great TAs. So far we have 4, but given that we currently have 200 students enrolled, hopefully we'll get some more. One is working on the camera, Samip. Maybe you can raise your hand. And can the other ones who are here also raise their hands? Are they? Oh, there's James. And I guess David I haven't met yet. He just signed up. And then Bharath is also one of our TAs. He's a PhD student. You already got the first part right, which is we'll be here from 3 to 4:20 in Gatesby 1. Generally, there will be 3 major problem sets, and there will be a lot of programming. So hopefully, and we'll get into that a little bit more, that is something that you're comfortable with already. We'll have a bunch of office hours. If we schedule them well, probably one every day. They'll start next week. All the ones from the TA start next week, but I actually will have an office hour right after this lecture in case you have any questions sort of around general organization already. The slides will usually be uploaded before the lecture. I'll try my best. Then the video of the lecture and the lecture notes will come right after. All right, prerequisites. We will require you to program a lot in Python. So hopefully you're proficient in Python. If you know C++, Java, and Lua really well, then that's fine too, and you can probably pick up Python, but ideally you know Python already. Otherwise you're going to want to start right now taking a bunch of Python tutorials. We'll do a lot of matrix calculus, taking matrix derivatives. That's not trivial for some people, especially if your linear algebra and college calculus has been either a long time ago or still in its infancy. So that is definitely a prerequisite. Basic probability and statistics. Hopefully you know a lot of the basics of those. And then the most ideal prerequisite is really CS229, having taken the machine learning class where you have basic understanding or got a basic understanding for cost functions, taking derivatives of simple functions, and then performing optimization with gradient descent. If those words are already somewhat familiar, then I think you will have a fun time in this class. Are there any questions about prerequisites? All right. Grading. Very fun for everybody involved. So the 3 problem sets will each count for 15% of your final grade. We'll have a midterm exam, which also only counts for 15%, and the final course project. And the final course project will, I think, be the most exciting part for you personally. Several students last year were able to publish papers, got into Hacker News and various other fun places with their projects. It's a very exciting time right now for deep learning, and if you do a really good job on those, on your final projects, I think that's sort of something that will last you for a long time in your career. We'll have a milestone where you basically have to at least have a project description. We'll actually give you a 2% bonus, 2% of the entire class grade if you have your data already and ran an experiment. And we do that because we really want to encourage you to start early on your class projects. Usually we will run experiments. Those experiments will take inevitably days or at least several hours to run, and if you start the night before, it's just impossible to get a good grade. So you want to start early. You also don't want to spend too much time, and we'll have a special session on just the class project in a couple of lectures, but you also don't want to spend too much time collecting the data and so on. You want to find quickly what is the problem domain that you have, and what excites you that you want to like to, you know, in natural language, or at least some of these related techniques, try to predict and automate. So I've last year found that several students who had a really great time came to a lot of the office hours, and then some students who didn't have a great time never came to the office hours. So this year we're going to try to make it a prerequisite or part of your grade to at least show up to one project advice office hour throughout the quarter. So it'll be a very simple thing like check mark once you came, we talked about your project, and then you're all set for that. There will be a final write-up project, and then we'll have a big poster presentation probably in the Gates lawn. And yeah, you'll get bonus points if you have exceptional fun poster presentations. We had last year, we had folks who had like live demos set up where they showed you something and then it described what it saw directly in language. Those are the kinds of things that if you're really getting into this, you could build, and those will get some bonus points. All right, late policy, we try to be very lenient. Basically, you'll have 7 free late days that you can use whenever you want. After that, we'll take 25% off per late day. You can use at most 3 late days per problem set, because we want to post potential solutions and discuss solutions openly in the office hours. And yeah, that does not apply to the final course project. You do have to submit that on time so that we have time to grade it. Collaboration policy, I guess, yeah, again, read your student handbook and codebook, and remember the honor code. And then, yeah, it's very important to understand what collaboration means, especially as we analyze your code. You don't want to have your code be looking too similar to other people's code. Any questions on grading?
If you use your late days, can you still get the 2% bonus on the milestone?
Yes. Cool. All right, so I want to give you a very high-level plan and overview of the problem sets, because they're going to be a major piece of the class. So I think if I sort of look at the class material the way we have it in from last year, the first half of the class will be quite hard, because you have to learn everything from scratch, and we'll actually make the first problem set also in pure or raw Python, just to make sure you really understand all the basics and mechanics. And then this year, we'll update problem set 2 and 3 to actually use a library called TensorFlow that was just introduced last year. It's a pretty brand new library that still has some problems, but I think the future for deep learning and practice will always involve some kind of automation, and libraries like TensorFlow or Torch. No worries if you don't know those yet. But these are basically becoming standard tools, and I felt it would be weird to make you do all 3 problem sets all from scratch in raw Python. So once you really got up to speed with problem set 2, which will be a pretty major neural network architecture, a very important one, so-called recurrent neural networks. Once you're up to speed in TensorFlow for recurrent neural networks, you're basically the world of NLP will be your oyster. Like, you can then all of a sudden do a lot of really amazing things. You will likely use that as part of your project to that kind of code, and it'll be exciting and really a very useful tool in your jobs, in your research, in all kinds of ways. But it's also non-trivial to get there. So if you have sort of high-level things you can plan throughout your quarter, make sure you're really up to speed through the second half, because then we'll also make problem set 3 a lot shorter, and because you then have the tool of TensorFlow in your tool belt, you'll be able to solve it, I think, relatively easily. So yeah, we'll again make problem set 3 a lot shorter so that you can have more time for your final projects. All right, so those were all the organizational things. Are there any questions around organization? All right. So then we can get started on deep learning for natural language processing. So very, very high level, what is natural language processing in the first place? So it's basically a field that is really at the intersection of computer science, artificial intelligence, and linguistics. And for us, the goal of this field will be for computers to process, or scare quotes, understand natural language in order to perform tasks that are useful. So for instance, question answering is a task that is incredibly useful. If you have a question about your iPhone, it broke somehow, and you want to know the answer, and we could have computers give those answers, that would be very useful and save companies a lot of money. Now, I use the scare quotes of understand because really fully understanding and representing the whole meaning and all its glory of language, or even defining it, is quite an elusive goal. There's a lot of philosophy of language, Wittgenstein, Frege. We won't go into any of those details, but we want to be realistic in our expectations. In the end, we will usually have a very concrete task that we think is useful to solve. And when we say meaning and understanding and reasoning and all these kinds of things, really we mean we have very complex functions that we learn to predict and solve some kind of useful task. So I will stop using the scare quotes throughout the lecture, but it's something to keep in mind. Really, perfect language understanding is kind of AI complete in the sense that it's inextricably linked to thought, and we don't really have a great way to represent all kinds of thoughts in a computer in all their fuzziness and concreteness and logical ways and so on. So what we'll look at very concretely are different levels that exist in natural language processing. It starts usually with speech, and then we use phonetics and phonological analysis to understand speech better. From there, we may go and look at morphemes, short stems, for instance, and prefixes and suffixes of words. Then we'll go to syntactic analysis, actually trying to understand how words are put together to form the meaning of whole sentences. Syntactic analysis is really more like the grammar, the structure and syntax of language. Once we have that, at least traditionally, we will then go to understand what the sentence actually means, and eventually we might want to use the sentence meaning to have a full discourse. Now in this class, we will not do much of OCR and simple things like tokenization. We will not focus on that. We usually will assume we have some speech, but really the major focus will be on syntactic and semantic interpretation. And in some ways, what you will notice is we might actually sometimes go directly from here's a word or a list of words to what does that list of words actually mean. We may skip some of these levels that have been traditionally thought to be required for understanding language and go directly to semantic interpretation, because that's really where the meaning is, and in the end, when we communicate, it's all about the meaning. It's less about the structure that we use. All right, so let's look at a really, really tiny subsample of NLP applications, several of which we will implement in this class and cover. So it starts with really, really simple things: spell checking, keyword search, finding synonyms in a dictionary, for instance, or a taxonomy. Then there's some intermediate tasks that are a little harder, extracting specific types of information from websites, for instance, finding product prices or dates or locations or people names. And I'll give you an example in a live demo at the end of this lecture. Or extracting company names that can be useful if you work in finance and you want to find which companies are mentioned in similar articles and hence might be related, to understand sort of company networks or people networks. Then still somewhat simple kinds of tasks are classifying longer documents for instance, the reading level. Should this be a text that is suitable for fourth graders to use? Or understanding the sentiment of longer documents in case you want to predict movie revenue, for instance, after you see a bunch of movie reviews when the movie comes out. So those are still relatively easy and intermediate tasks. And then the really hard ones, which we'll also cover in this class, are machine translation, which really captures a lot of the complexity of language. Being able to translate from English to German or Chinese or any other language is really hard, and is really also one of the tasks that we haven't solved in any kind of sufficient ways such that we can say we're better than humans. And some people think that that might be one of the most elusive kinds of tasks, being able to better translate, because you may need to know so much about life, love, and God and everything, the whole world, to really be able to translate subtle nuances in novels and things like that. But there is interesting research actually from Stanford and the NLP group here that shows that having at least an automated raw translation from a computer will speed up the work of human translators significantly. And so it is definitely something that is getting more and more useful and more used in daily life. We'll touch a little bit, but not too much, on spoken dialogue systems. It's something that's very hip right now in industry. A lot of people think that that might be one way you might interact with a lot of different companies in the future. Instead of having to email somebody or call somebody, you can just type in a chat window and or speak directly and have an algorithm or a deep learning model essentially communicate with you. And that kind of leads us also to some complex question answering problems, where you might require logical reasoning to answer a question. You may have to read a bunch of materials in order to be able to really give an accurate answer to a question. So I guess I mentioned a couple of these already, but here are some more real applications that you see in industry, and a lot of them actually in this area. Of course, we all know search, in both written and spoken search nowadays. Online advertisement uses a lot of natural language processing to understand language. Automated or system translation I already mentioned, doesn't always work that well. Sentiment analysis is a very interesting task because it's one of those general classifiers. If you once train a really good, accurate sentiment classifier, you can use it across a whole host of different tasks. You might want to understand movie reviews, but you might also want to understand customer sentiment, like this customer is really angry when they're complaining about something. That too actually has some interesting pitfalls. So here's an example where Anne Hathaway starred in a movie that had really positive reviews, and then right after the positive reviews came out, the stocks for Berkshire Hathaway, the company, surged a lot. And so we know already that people are using automated sentiment analysis to financially trade, basically, do automated stock trading. And in this case, they didn't do what we call entity disambiguation properly. They didn't realize Hathaway was the person here and not the company. So there's still room for improvement, and it's clear that there's a lot of interest for these kinds of techniques in industry. So why is natural language processing so hard? Why do we need a whole lecture? Why can't we just take some standard machine learning techniques and apply them to text? Well, I guess I touched upon this a little bit, but there's a lot of complexity in representing learning and using linguistic, situational, world, and visual knowledge. So when we try to understand language, it touches also on the visual world, some meaning that we have, for instance, grounded. So we ground the meaning in the visual world. So what's the meaning of green, if not something that we as humans can see as green, right? That's a simple example. Now, there's also a huge amount of ambiguity and world knowledge that you need to, for instance, just understand this very simple sentence. Jane hit June, and then she fell. Now, if it's fell, who do you think she refers to? That's right. But if she ran, then she probably ran after she hit her, and then it's Jane. So the verb that comes after this word basically helps us to do so-called anaphora resolution, basically understanding what this pronoun here refers to. And basically it could be either Jane or June, depending on the meaning of the verb that follows it. And traditionally, when people started doing natural language processing way back in the 50s and 60s, they said, well, I can just define the list of all these words and then I will know. And I will be able to make computers understand language. And that just failed miserably because there's so many exceptions, there's so many different words you could try that, and there's no way you will ever be able to write down by hand all the rules of language and how you would understand it. Here's another really interesting example of ambiguity. I made her duck. So let's see if we can come up with a couple of different interpretations of that sentence. So the simplest one, well, I don't know. It's actually, it highly depends. It's even a little culturally dependent. So does anybody have a first interpretation of I made her duck and describe it in like a different sentence? Yeah.
I cooked someone a dish that is consisting of duck.
That's right. So that's the first one. I cooked her a duck.
I made her physically duck, yeah.
That's right. You like, you know, swing a bat or something accidentally and she had to duck. What else? Yeah.
You transform her like use some magic.
Interesting. I would say I made her a duck, but yeah, I could see that. Yeah.
You created her pet bird, her duck.
That's right. You carved maybe like a duck out of wood, and you made her a wooden duck by carving. And maybe there's one more. Yeah.
You turned her duck into a vague man.
Whoa. Maybe. So I guess the last one might be you actually made her duck, like the one that she bought, right? And so all these are subtly, like some are obviously different, completely different, and you may want to see a picture, for instance, to understand which one you meant. The beautiful thing about some of the techniques that we'll cover in this class is that they actually transfer very quickly between language and vision, and so you can actually use and combine these techniques, especially if you've taken, who here has taken 231N last quarter? Awesome, so roughly half of all the people. Okay, so you will be able to see that a lot of the techniques will transfer. Hopefully some of this will be boring and you'll be able to do it very quickly, but there'll still be a lot of things that weren't in that class. All right, so what is deep learning? It's essentially a subfield of machine learning and basically tackles the following problem. That most machine learning methods work really well because it turned out that there's human learning or graduate student assent to try to find really good features to give to the algorithm. So for instance, if we're trying to find named entities like locations or organization names, one of the state-of-the-art methods in not too long ago, 2010, basically had to give all these kinds of features to a machine learning algorithm like logistic regression or conditional random fields to make a very accurate prediction. So it had to look at word shape, for instance. So it had features of like, is the first letter capitalized? Is every letter capitalized? Is there no letter capitalized? And it had one discrete feature for each of these kinds of problems. Or it looked at the current part of speech tag, in short POS. Is this a noun, a verb, an adjective, and so on? Or is the word in front of it an adjective, a noun, a preposition, and so on. Basically, a lot of different kinds of features were given to the algorithm, and only then was it able to find, oh, this is a location, this is actually a city name or something like that. Now, that's not very attractive if you try to build an algorithm and you had to actually manually sit down and look at all the data and all the examples and say, well, it's still making this mistake. Maybe I should add this kind of feature to solve that specific problem. Because that way, it will be very dependent on the kind of text that you're looking at as a human. And in many cases, it will actually be too specific to that data set that you're looking at. And then if you have another language or another kind of data set where now all of a sudden the people are from a different country, and you have to look again and manually look at over all these features. And the beauty of deep learning will be that we'll actually try to automate that process. So when you look at machine learning in practice, it used to always be that you spend the majority of your time describing your data, looking at how to basically make sense of it to a computer such that it can just kind of optimize a very simple function. And at the very end, you'd have the learning algorithm. And this is even a sort of optimistic way. Some people might say it's really 90% to 95% of you sitting down, becoming an expert in your domain, and then classifying or making certain kinds of predictions. And really, the learning algorithm is just very simple optimizing of weights, or basically saying this feature matters this much for this example. And it used to be that really to do the overall process very well, you kind of had to have a lot of experience, maybe even a PhD in that specific domain to do well overall. Now, in deep learning, we'll basically try to learn these representations. And you can see deep learning as a type of representation learning, which essentially attempts to automatically learn these features or representations by giving it the raw data. Raw data in the case of images was just the raw pixels. In our case, it will be just the raw words, or even lower level, just the raw characters. And then you give it the raw characters, you say this sentence is positive, this sentence is negative. You give it thousands of examples of positive or negative sentences, and then you ask the model to figure out which words seem relevant, which order of the words seems to matter. This was, not a good movie, but well, yeah. So is not before the adjective and then becomes negative or things like that. You don't want to manually define any of that stuff. You just want to give it a lot of examples and have it figure out how to describe it and then make a final prediction. And what we'll see a lot, and no worries if you don't understand this figure yet, is that these deep learning algorithms will essentially attempt to learn automatically these multiple levels of representations. Now, sometimes we will be a little fuzzy with the term deep. Turns out, for instance, next lecture we will go deeply, no pun intended, into word vectors. But word vectors are not going to be actually deep models. They're actually going to be very shallow models. But there are ways for us to start seeing everything in the right kind of light and with the right kind of mindset. All right, any questions so far about deep learning, what we'll cover, applications that you're excited about and wondering if we'll cover it or not? All right, so a little bit on the history and the term of deep learning. Deep learning actually also includes a lot of so-called graphical models and probabilistic generative models. We will not focus on those. We will focus the entirety of the class on the neural network family, which is really now the dominant model family inside the field of deep learning in research as well as in industry. You might be a little snarky and say, well, this whole deep learning thing and neural networks, isn't it just kind of clever terminology for combining a bunch of logistic regression units? And if you've taken, who here has taken CS229? All right, excellent. All right, we'll have a great quarter. So you've are familiar with logistic regression, and one thing you will notice is that throughout the classes, really we'll have a lot of logistic regressions kind of put together in all kinds of different ways. And that is really it. And so there's some truth to this. At the same time, there are a lot of interesting modeling principles, such as end-to-end learning. I give you the raw input, I give you the final output. You learn from the final output all the way to the raw input and everything in between. Really putting the artificial back into artificial intelligence, if you will. It was really a lot of human intelligence that went into a lot of these different applications. And in some cases, there are actual real connections to neuroscience, though I have to say that we will not go there. This is not going to be a neuroscience class. I'm not a neuroscientist. I published once or twice with some, and I know some things, but I really, the neural inspirations of these models are very high level and fuzzy. Especially for natural language processing, where I think we have even less of a good understanding of how the human brain really represents and processes language. At least compared to the visual cortex, where there are a lot more clear sort of this neuron actually does exactly that kind of thing that exists rarely or ever in natural language understanding. We'll also not be taking a historical approach. So There will be some folks online who say, oh, but hasn't this been, discovered already like 30 years ago by this person? And in many cases that will be true, and I'll try to give you the links, but I'll not ask you to read sort of historical papers. In many cases they're superseded, and while a lot of the very core ideas of deep learning have been around for several decades, there's still a lot of new techniques, and I think you can get a lot out of this class without necessarily knowing the full history of it. But if that is something that you're interested in, there's a great sort of long journal version of deep learning and neural networks, an overview by Jürgen Schmidhuber, who's done a really great job discovering all the intellectual history of the field. All right, so now why does it really make sense for you to take this class, and why am I so excited to teach it? I mentioned a couple of these before, but basically the field of AI had really been a lot about understanding your domain incredibly well and then designing features that often turn out to be overly specific to the problem that you were looking at, or incomplete because you can't look at as much data as computers could, and it took a very long time to design and validate those kinds of features. On the other hand, with deep learning, we will learn these features, and that will make them easier to adapt, much faster to learn, and literally you will be able to solve problems in this class in your project that used to take 2 or 3 years for teams of 10, 20, up to 100 people, depending on how good you are in your project. And do this fully automatically. It's quite magical if you know sort of 10 years ago how long those kinds of things would have taken. Deep learning provides a very flexible and almost universal learnable framework for representing not just linguistic knowledge, but also world knowledge and visual kinds of information. And deep learning will also, and we'll see that starting next class, be able to learn in an unsupervised way. We'll just give it a bunch of text, and it will figure out interesting relationships and the actual meaning of words, just from looking at a lot of raw data. But then also, and that's where usually a lot of the power is, it's very, very good on supervised problems. So trying to very accurately predict a certain outcome. Are there any questions about these things so far? Yeah?
So is it like we need to prepare many features and deep learning is going to figure out which features are important, or like it's going to also like find combined features that are affecting the output rather than the individual features? How does it?
It's a good question. So the question is, will we give a lot of features to the algorithm that will learn how to combine them? And the answer is, we'll actually just give it the raw words. In our case, for this class, it could also be the raw speech signals, or raw pixels, or a combination of all these things. And then it will learn how to combine them and how to combine the features of those features in various different deep levels. So it will be completely, in the end, automated. You just give it raw text, a model specification, what output you'd like to predict from that text, and it will learn all the features and combinations of them automatically. Yeah.
How well can we describe the meaning of these learned features?
So we'll actually get to that in a couple of slides to give you some idea. And many times we can actually project them down into a 2-dimensional or 3-dimensional space that we can visualize, and then we will actually see very interesting patterns that emerged from these models in often unsupervised ways. So there will be some ways we can visualize it, but it's also almost part of the art. Sometimes you get to know a model really well, and you get to like sort of tune it to work really well. And then others will actually come later and say, well, this model works so well, but we don't really know why. So they then analyze it and visualize it, and it becomes sort of almost a research problem in and of itself. And people have been able to come up with very interesting visualizations and interpretations of these models. Yeah?
Probably related to that, but when you talk about representation of information of various types, are you talking about representation at the output level, or are you talking about representation in the middle layers?
So the question is, when we say representing and middle layers, I guess we haven't really defined a lot of those terms, so you're probably a little ahead of the class, but we will do both. The final output is often very simple. Is this a negative sentence? This movie sucked. Is this a neutral sentence? I had watched this movie. Or is this a positive sentence? I love this movie. It's the best family movie ever. Those kinds of final representations are very easy. They're just like a binary output, or a small vector of saying, these are the probabilities for these three classes. So that kind of representation is the easiest one to interpret and to learn. But we'll actually also look at intermediate layers. And for instance, the very first layer, which will be word vectors. All right, now you might think, well, if some of these techniques have been around for so long, why is this so relevant now? Why is this only the second time this class was offered for deep learning for NLP and not, the 50th or 10th time? It basically started roughly in around 2006 that deep learning techniques actually outperformed these traditional machine learning techniques. So up until then, it was really all the hand-designed features that did so well for all the different tasks that you were using. And even 2006, you were probably already using a lot of machine learning when you used a search engine or something like that. So why now? Basically, deep learning techniques benefit a lot more from the data, because we will ask the models to learn the features by itself. It also requires a lot of data, right? If you only have 10 examples, and this is already kind of relevant for thinking about your class project and how to get started on that. If you only have 10 examples for something, and you ask the model, you know nothing about language, right? The model starts being a completely random gibberish kind of algorithm that doesn't make any accurate predictions, and you only give it 10 or 15 examples, it won't be able to understand all the complexity of whatever domain it is that you're trying to describe. However, when you give it millions of examples, then it can start to figure out all these patterns by itself without you hand-holding and describing these various features. And so deep learning techniques in somewhat benefit, but also require a lot more training data. Then we'll have a lot of faster machines, and especially multi-core kinds of architectures. We'll notice down the class that a lot of the things will boil down to making very large matrix multiplications, just W times X. And it turns out that those are very easily parallelizable, and so if you have multiple cores, you'll be able to make use of those. And now some of the GPUs have 4,000 cores, and it turns out with deep learning techniques, you can very efficiently use those 4,000 cores and parallelize very nicely. And then, and this is sometimes overlooked, but I think it's quite relevant, especially for natural language processing. In the last couple of years, there have also been a lot of new models and algorithms and optimization techniques and ideas that helped us make use of these very powerful techniques. And that overall resulted in just much, much better performance and accuracy, especially for tasks, such that they now become really viable to be used in practice. And it started with speech and computer vision, but now has definitely arrived in natural language processing as well. So let me give you at least a very sort of one slide per breakthrough kind of overview of how we got to where we are. Basically, it started out with deep learning for speech, where we had all of a sudden very large data sets, and basically we're able to take in not quite just a raw frequency, but some very raw features of the sound, and then basically predict phonemes and words. And here we see a word error rate, and the word error rate really dropped significantly. So when you actually now speak into your phone, your Android or your iPhone, you will very likely use a neural network in the back end that actually understands what you're saying. And if you tried speech recognition like a decade ago, it was for the most part a joke. And it's really now that it's become so accurate that you actually, it makes sense to talk into your phone, even sometimes with noisy backgrounds. The other breakthrough, and this was what all of 231N was about, is basically, or had been in computer vision. And really, computer vision was also what most deep learning groups had focused on up until maybe 2 years ago or so, the majority of their efforts. And so we understand neural network models a lot better for images. So we know, for instance, when you take in the raw pixels, the first layer of a neural network basically finds little edges. And then once in the second layer, we will combine some of these edges into more complex textures and shapes. And then in the layer 3, you'll have more complex, even more complex kinds of combinations, and maybe you have neurons that fire when they see a tire and things like that. In natural language processing, we won't have beautiful visualizations like that, unfortunately, and there won't be as kind of obvious connections of, oh, we put these two characters together and then they form kind of this positive meaning or something like that. But we will have some visualizations also that help us understand, and we'll see that in images, it is, in text, it will be very hard to understand exactly what one word would be represented as. So for instance, the example of duck. Let's say we try to represent duck. Should it now be close in our representation to a lot of verbs, like hiding and things like that, or should it be closer to other bird names, right? It's unclear. And so you already kind of see that the language understanding and representation part is often much more complex than the visual one. So basically, when we say deep natural language processing or deep NLP, we want to try to combine these two ideas and goals. Basically taking the goals of natural language processing and then try to use representation learning and deep learning methods to really solve them end to end. And so in the last half hour or so, I will go through a couple of these representations that we have for the different levels that we mentioned in the beginning: speech, morphology, syntax, and semantics, and give you a very high-level overview of what we mean with these different levels. And then we'll also cover a couple of applications that have already been transformed by deep learning. Are there any questions so far on the related kind of subfields of deep learning?
Is there a way to augment data for NLP problems?
So it's a pretty sophisticated question already. So in computer vision, what we often do is, instead of giving it just the raw pixels, we may change the input a little bit and we rotate the image, because we know, well, if this is, for instance, a quail, well, if I rotate that image a little bit, it's still a quail. So we can have these input transformations. Don't worry if you don't follow this yet. We'll get to that in a little bit, or well, in several weeks. But basically, it's much less obvious how to do that in NLP. I've actually tried it a little bit in research, and I haven't gotten any big gains like the ones you see in computer vision. That's the short answer of it.
I guess to follow up on that question, we could substitute with like synonyms and things like that.
That's right. But what we'll see is that that is already captured pretty well by the deep learning models themselves. So. All right, so let's go through these different layers of representation, and let's start with phonology. So originally, if you try to understand words from spoken language and transcribe it into written language, and you study linguistics, you would basically take a whole quarter on phonology, where you basically have here the International Phonetic Alphabet, and you try to find all the different, define all the different plosives, for instance. So b is a plosive, and you have fricatives, that's exactly the kind of sound that you'd see in those, or dental, where you actually use your teeth, like so. This is the little theta, and so on. So you basically would spend a lot of time trying to describe all the subtleties of how human sound can be transcribed, and then basically try to automatically predict one of these discrete categories. Now, in deep learning, what we'll do instead is just describe it as a vector, a list of numbers. And we won't try to make any of these fine distinctions between the different ways to pronounce a word. Now, moving on from just knowing what the sounds are, the next level might be understanding morphemes, which is basically the science or field of morphology, where we might want to understand a word like uninterested might be chopped up into a prefix un, and you see that prefix modifying lots of different words and changing potentially the meaning later on. You have the stem interest, and you have a suffix. The suffix in different languages can change, time, for instance, so interesting versus interested, and things like that. Now, again, in deep learning, every morpheme will just be a vector, a list of numbers, and we will train a neural network that just combine two vectors into one vector, and then we hope that the resulting vector captures whatever we need to capture for our task. So this is modeled by Tang Luang, one of the PhD students in the Stanford NLP group, and he had used a so-called recursive neural network. It's also a family of networks we'll cover in this class, that basically combines just a list of numbers that represent un and one that represents unfortunate, and we'll combine those two to unfortunate. And we won't make any kind of explicit assumptions about what unfortunate should look like. We'll just let the model figure that out. So now word vectors, you won't see them very well, but I'll zoom in a second. The next level after we understand sort of the parts that words are combined from, we want to understand the words themselves. And I'll zoom in a second, but basically with unsupervised deep learning techniques, we'll understand that certain words are similar to one another and they're in certain relationships. And so we will go and we will learn just by giving it all of the text of Wikipedia, for instance, and we'll find neural network or even more shallow, very simple techniques to learn to map words also into a vector space. So this is really going to be one of the fundamental ideas and the first main idea of this class, and one that we'll see throughout this whole lecture. As long as we can map any kind of input into a list of numbers, we're going to be in the world of deep learning, and we can use all these different techniques. And so words will also just be lists of numbers. And usually we'll represent a word in something like 50 or 500 dimensions. Of course, we can't visualize those. And if we want to understand what's actually going on inside the model, what we often do is project them down to 2 dimensions. And then we actually see interesting patterns, for instance, that countries all map into somewhere similar sub-area of this high-dimensional vector space. And for instance, companies like France and Germany that are actually close to one another in some fuzzy way, geographically, also culturally, maybe a little bit. Interestingly enough, their vectors are also closer to one another than other countries that are further away. And those might be also more similar again to one another. And these are things that will be learned automatically from just giving it a bunch of raw text. And again, you'll see that it doesn't always make sense. There will be problems when you represent everything as just a single list of numbers, a single vector, but it will be very useful to solve a lot of different tasks nonetheless. Here are a couple of verbs, and say, think, and expect are closer to one another, for instance, that coming, come, go, and take, and get, and so on. Here we have a bunch of auxiliary verbs, are, is, were, was, and those are close to one another too. Now, once we understand how to represent words, words in isolation are not that useful. Usually when we communicate, we combine words into longer sentences. And so traditionally, people would describe sentences with very discrete structures and discrete tree structures like this one here. So the house at the end of the street is red. We might say the is a determiner, and don't worry if you don't understand all that linguistic terminology. We'll go through it as we go through the class. But basically, the is a determiner, street is a noun, and that together combines into this discrete noun phrase. Now, unfortunately, just saying this is a noun phrase, it's not that useful, right? You still don't really know what does it actually mean, the street. How does the street relate to the road, or the side alley, or the alleyway in which I was born, or things like that. Like, it's very hard to capture all of that in one discrete category, but that has been sort of traditionally the way to describe syntactic categories, just the structure and the grammar of language. And so in the end, you might say, all right, that whole thing is a sentence, and the sentence is just the category, the discrete category S. Now in deep learning, and you'll start to see the pattern here, since we're already describing all the words as vectors, we'll also describe all the phrases as vectors. And then we can actually compare the cat, for instance, the phrase the cat, with the phrase our dog. Right? Now they're not just a noun phrase, but we'll actually have a vector, and we hope that the vectors for phrases that are similar are also similar to one another in some way. And again, because every word and phrase will be a vector, we can use standard neural networks, standard functions that map vectors to other vectors to learn to make certain kinds of predictions. Now, let's go to the next level above, which is semantics. Traditionally, and this is again, we're going through sort of a long history here of the whole field of linguistics, and again, morphology, phonology, syntax, semantics. You can literally have 1 to 4 quarters of classes about each of those separately. So we're sort of not doing them complete justice, and they're actually very interesting in and of themselves. But if you're trying to make predictions, trying to have a computer automatically understand and make predictions based on the inputs, it turns out we can, in some sense, get away with not having to understand all these subtle details. We can just make the computer do accurate predictions without us understanding all the subtle notions of these different layers of representation. So let's look at semantics. If we, for instance, try to understand the sentence Mary likes Sue, then if you took a semantics class and maybe then another advanced semantics class, you would go to eventually what we call lambda calculus, where you say likes is this complex function that takes as input some other variable y, and then takes as input another variable x, and then can basically combine these different representations. And don't worry if you don't fully follow this, but if you know a little bit of functional programming, there's actually a lot of connections to those. So here you might say Sue, for instance, is just represented as some discrete symbol s. And when we combine Sue with the verb likes, then what we'll get is basically a reduction here of lambda, and now we'll get this thing, which will, this expression is lambda calculus expression, where we replaced one of the variables, the free variables, with this concrete term s. And then if we combine Mary here on the left side, we'll replace that variable x with Mary. And in the end, we have this discrete representation likes m comma s. Now, of course, again, if we try to ask, well, how similar is now that sentence, Mary likes Sue, in that representation to the sentence, Mary and Sue enjoy hanging out together, right? Like, that sentence already will be quite tough in lambda calculus to represent, to be represented. And they're very discrete. They're not sort of fuzzy, long lists of numbers, and we're not in a vector space, but we have very discrete representations. And so there's no notion of similarity or the fuzziness of language when we use these kinds of representations. And now in deep learning, again, every word and phrase and even every logical expression will just be a vector. And because of that, we can combine different vectors, again, using neural networks, into other vectors. And then we can still, it turns out, make it a classification problem. For instance, we could say all reptiles walk versus some turtles move. And then we can ask, well, does one actually logically entail the other? Well, if all reptiles walk, and we know that turtles are reptiles and some of them move, then this clearly has to be true if this is also true. So this is the entailment problem. This was studied by Sam Bowman, who happens to also be a Stanford PhD student in linguistics. And basically, instead of us having now to define, oh, well, turtles are subsets of reptiles, and moving is a general expression, and walking is a special subtype of moving, and any of these things, he basically just says, everything's a vector. Let me just train a model with the final output that I care about, with a simple logistic regression at the top, and just say, yes, no. These two sentences are in this relationship, or they're not, and I learn everything in between. And eventually, amazingly, the model, without us having to manually define that, you know, reptiles is a supergroup of turtles and moving is, you know, basically more general than walking, without us having to define any of these things by hand, the model figured it out to make the final correct prediction that one entails the other. Yeah.
How many examples did you use to train that?
You do need a lot of examples, right? You basically, like in the thousands. Generally, if you, for any of your projects and any kind of deep learning models, if you have 1,000 examples for each of the types of things you try to identify, then you start having a chance of having a deep learning model learn it. If those 1,000 examples are good representative examples of your overall problem. Yeah.
Would you lose some kind of like alignment information? Because traditionally in the semantic lambda calculus, the difference is going to be all and some are going to be very two different lambda expressions.
Mm-hmm.
And actually matching them one-on-one is one of the ways that humans do compare them, do entanglement relationships. So do you think this kind of like tree composition structure might not be the best structure?
It's a great question. So here we actually said we first combine all in reptiles and then say all reptiles now is combined with walk. And here we say some turtles, and first you try to represent the meaning of some turtles, and then you combine it with move. Now, it turns out that you don't even need to have the tree structure. Eventually, we'll just read words from left to right, and we'll do almost as well, in some cases better, in some cases only slightly worse, to having this complex grammatical structure where you understand that so why do we have the tree structure in the first place? And again, we'll have a whole lecture on just understanding tree structures better. But generally, you wouldn't say reptiles walk and then say all of that, right? It is much more intuitive to say this sentence first basically describes an agent or basically a noun phrase, and then you say now all of these reptiles, all reptiles, and then you combine that with walk instead of saying reptiles walk and then adding all after that. And so this is kind of the very, very high level idea of syntax and grammatical structure. And we won't need to go into too many details of that, but yes, sometimes the trees help, but not always. Yeah?
Is the claim that a properly trained model has different layers that actually does these things, or is it that with proper training you can mimic each of these levels with like an appropriate net?
So it's a little advanced of a question to really answer it. I think we'll need more time and sort of a lot more of the knowledge that we'll cover in this class. In the end, the hope is that if you don't have the tree structure, but you think it is required for the problem, that you will actually learn it sort of not subconsciously, that's would be a lot of scare quotes, but implicitly. That if you just go from words from left to right, that the neural network keeps some kind of simple stack, for instance, and some neurons will capture, oh, now something happened, and now keep these things into, put them into this subspace and things like that. So we'll get into that a little bit more, sort of half of the lecture, half of the quarter. And but yeah, that's a short version of that answer. It's not very satisfying yet, but I guess that's why we'll have the class. All right, so we basically were able to see that for all these different levels of linguistic representation, starting from speech to phonemes and morphemes, words, phrases, grammatical structure, and the meaning, everything will essentially be mapped to a vector. Now let's look at a couple of applications. So here's one for sentiment analysis. And just again to help you understand how amazing it is that we'll be able to do in this class, and we'll be able to build some sentiment analysis models that are very, very accurate. I'll tell you a little bit about traditionally what it meant to do very well in sentiment analysis. Basically, you had to have a curated sentiment dictionary, and you said, well, if we try to do this really accurately, let's all sit down and think about all the positive words that we have. Wonderful, awesome, amazing, great, sweet, and so on. And then you look at your errors, you say, all right, now let's just basically sum up positive words and sum up negative words. And for each new sentence, we say if there are more positive words than negative words, we say this is a positive sentence. And that's our algorithm. Very simple algorithm. We look up something in some dictionary and do that. And then in that kind of project, what you would notice once you look at the errors that your algorithm makes, you see, oh, well, there's also negation. Right? And so I'd say, well, if I see any of these positive words and then I see not in front of it, I'll just say it's negative. So not good, not wonderful, and I'll say it's negative. And then you look at that and you say, well, not awesome, but still okay. Might actually be not negative, but it might be neutral or just slightly less positive, right? And you keep doing that until you realize you're never going to actually be able to write down all the rules by hand. Now what we're able to do is we basically give it a lot of examples of phrases and sentences, and we can train a single model that takes in these raw labeled phrases and makes a final prediction, and then was able to outperform all this human engineering of this domain of sentiment. And here's again an example. Unfortunately, we're missing all the trees, all the lines for the trees. But basically here we have humor is very positive, somewhat sadly intelligent humor is not as positive as just humor. But basically this whole phrase intelligent humor is identified as positive by this model. Now any other kind of intelligent humor is still positive. Cleverness and wit or other kinds of intelligent humor is positive. To care about all these positive things is still positive, but then, or neutral here, so this is a misclassification. But then once the movie doesn't care about them, the algorithm learned that now it's actually negative. So not caring about a bunch of positive things turns out to be negative. And again, we didn't have to give the algorithm this kind of rule, like not caring about positive things and so on. It just learned it automatically. Yeah.
Are you always initializing with like some sort of word to pre-trained word for that here? Or
yeah, I see you'll have a huge discrepancy of people who are super advanced already and know word to vec, which is what we'll discover or describe in the next lecture. And then we'll probably have some people who don't know this yet. The short answer is almost always yes, unless you have a lot of data, and then you don't need to do it. And don't worry if you don't understand the question or the answer yet.
What's a lot of data?
Tens of thousands of examples at least per class. Yeah.
what if you have mostly positive training data? Like in this, like if you had mostly positive sentences, could you kind of still infer the negative sentence?
So it's a good question. So in general, you might remember some lessons learned from your machine learning class, and one of the problems in standard machine learning is this one called skewed class distribution or unbalanced data set. And deep learning is not immune to that problem. If you have 95% of your data is in one class, like 95% of all your sentences are super positive, and you have only 5% of your data set of sentences that are negative, your algorithm, even if it's deep learning, will still have a hard time learning that well, and we'll have some techniques that we'll cover sort of much later in the class on how to deal with skewed distributions like that. But yeah, neural nets are not immune to that problem. All right, so now let's go over another example, and then I think we'll only have 2 or 3 more, and then we'll end with a live demo of a very powerful neural network model. So question answering is one of these really tough problems in natural language processing, where generally you'd need a lot of feature engineering in past methods, and even in methods that are as little as 2 years old, where you may have to have regular expressions, for instance, and finding specific features is like a main verb. Does it trigger something very specific because you have a WH question for a subject or an object and things like that, or you define who's the agent of that sentence and things like that. So pretty complex kinds of features that you have to engineer to do well. And basically, in deep learning, there's some folks who use the exact same model architecture, the same kind of neural network architecture that we use in morphology, in syntax, in logical, semantics, and sentiment. In this case, it was a recursive neural network. The same kind of recursive neural network that was used for all these different levels turned out to also be able to answer questions for more complex kinds of things. And in the end, it stored a lot of the facts that were asked about during training in vectors. And so when you zoom into, again, these visualizations, the model had automatically learned that Ronald Reagan, Jimmy Carter, and Woodrow Wilson, for instance, are all somewhat similar. Now, how exactly they're similar, well, we know, but that again requires world knowledge. But somehow the model was able to say, in this area of my vector space, I represented in some combination of numbers that these were former US presidents of maybe a certain time frame. Right? And we didn't have to go in and teach it about, what presidents are and what time frames and different times are and so on. And it put, for instance, George Washington, Thomas Jefferson, and John Adams in yet another part of the space, and those are closer to one another and they're closer to other presidents. But if you go over here, you'll have, for instance, policies or explorers and emperors or wars, rebellions, and battles. So these are all kinds of questions that were asked during training, and those are in a completely different part of the space. And again, the model learned that automatically just by having asked and seen a lot of answers for different kinds of questions. Yeah?
Did the computer generate those labels?
No, this is basically the authors, Mohit Ear and folks, basically trying to understand what the actual algorithm learned when it mapped these different entities into a vector space. And it basically nicely showed that they cluster very well together. Yeah.
Are these clusterings dependent on how you project down the dimensions?
Yes. So depending on how you project down your high-dimensional vectors into 2 dimensions, things look slightly differently. But usually you see the same kinds of groups, no matter whether you use TSNE or PCA. Don't worry again if you don't know this methods yet. We'll cover a lot of that. Yeah.
You need to know that William McKim is a single instance, or can the algorithm learn that this is a single name?
Can the algorithm learn what?
That these two words belong together and should be in the
Those things can also be learned. In this case, they actually just learned that there are certain entities, and each entity just had one vector. But you could learn the combination. All right, now machine translation. I mentioned that was one of the toughest tasks in NLP. And again, just to give you a very high-level overview of the history, there are a lot of different techniques that people have tried to translate from one language into another. Some people said, well, first we need to, maybe we can just directly translate from one sentence to the other. But then people said, no, we first need to understand the grammatical structure. And then from one grammatical structure, we can translate to another grammatical structure. And others said, no, what we really need is to understand the meaning first, and then we can translate easily from one meaning into another language, that same sentence. So they're traditionally extremely complex kinds of models that require hundreds of gigabytes of RAM if you want to keep them in RAM, for instance, because they have to store all possible phrase pairs and things like that. It's very complex models. And they're, it's a huge area of research. A lot of us use machine translation. It's one of the most useful tasks in natural language processing. And it used to literally require many years and many different people to build systems that were at all decent. And none of them are still great. Nobody in machine translation comes even close to human translation. But even for like reasonably, decent systems, it was huge efforts for many years. And now I might ask you, what do you think is the interlingua, the sort of main way to represent language if you want to do translation? Vectors, that's right. So everything will be mapped into a vector, and we will go over this model in a couple of weeks where you basically take any kind of input language, you map it with a neural network into a single vector, and then you translate, and from that vector you generate the translation sentence. So if that doesn't convince you that vectors are useful, then nothing will. So yes, there will be always fuzziness, right? Duck, should the vector be here, close to hiding? Should the vector be here, close to bird? But in the end, when we look at these kinds of impressive applications, we will see that no matter how we represent it internally, it's just incredibly useful. And so to give you one idea of this, I actually have a little demo of a model that can basically be asked any kind of question, and it's the same kind of architecture that underlies all these different applications. So I can ask, for instance, what is the sentiment of this kind of this sentence? The best way to hope for any chance of enjoying this film is by lowering your expectations. So this is one of those really hard sentiment examples that we literally only in the last half year are able to consistently correctly predict. And the algorithm correctly says that this is negative, despite having lots of great positive words like best and hope and enjoying. But in the end, to do all these things, you have to lower your expectations, so it's negative. We can also, here's another sentiment example. The film starts out as competent but unremarkable and gradually grows into something of considerable power. So even subtle notions like that can now be learned, and this is all learned with a single architecture, which we'll come to only at the very end of this class. It's called a dynamic memory network. It combines recurrent neural networks, which we'll learn about in this class, but then it also needs attention mechanisms to focus on specific words while we're making predictions. It's a pretty complex model. We'll cover it towards the end of the class. And the same kind of architecture, we're also able to ask what are the named entities. And here we see it basically will tell us what locations are, what are organizations, and also people. Then we can also ask it what are the part-of-speech tags, and it will basically give us an output at every word, finding all the different nouns and verbs and determiners and so on. We can also ask it very logical questions. And again, it's the same kind of architecture. And it's an architecture that if you start early, you could probably implement in this class, especially if you come to office hours. Here is a story, a bunch of inputs, and we'll represent all of these inputs with just a simple vector representation. And we might ask, where was Mary before the bedroom? After we give it all these different facts. And amazingly, the model is able to reason over these different facts and basically come up with, well, first I pay attention to where she was this morning, and then I find things like yesterday. And because yesterday happens before this morning, I now give you the answer that it's cinema. And we didn't require any logical expressions of like, here are temporal words, and I combine these temporal words this way. We just gave it a lot of training examples. Here's a story, here's a question, here's an output answer. You figure out what you need to focus on, what temporality means, or any of these things. And then it represented it all in a vector representation, just a list of numbers, to give the final answer. Now, we can also ask, we give you this story, and I'll give you a second to see if you know the answer. Does anybody know what the answer would be? I think I heard it. That's right, yellow. And so if we ask this question, what color is Bernard, we really have to look at the input multiple times. In the first iteration of asking the question, what color is Bernard, we might just find Bernard is a frog, and that's what the model pays attention to. But it doesn't yet know the answer. It's still, from just knowing that he's a frog, you might not know the answer. But then it goes and finds other sentences about frog, and going over the inputs again, realizes Lily is a frog, still knows it's not enough, but now goes and finds Lily is yellow, and then actually transitively reasoned over these different facts to give us the final answer. And that kind of thing, that used to require humans sitting down and defining what's transitive logic. How do you go from A to B to C and then know that it goes to A to C too? And now all you need to give it is a bunch of vectors and represent that, a bunch of these kinds of input stories, in this case question, answer, input triplets, and the model figures it out. maybe to show you how general this is, again, you don't need to have any knowledge about the language. In some kind of almost sad way, it's just a bunch of IDs and we learn vectors for each character or for each word. And we can make very accurate predictions at the end. So I'm not going to make a fool of myself trying to read that out loud, but I think it's kind of a fun sentence. And again, question answer input triplets represent everything as a vector, make very accurate predictions. Same thing, translate. Question is, translate to German, give a bunch of question input triplets, and you can build a translation model. And last but not least, if you've taken 231N, you're going to be able to combine these techniques and even ask questions about images and also get answers for that. And it turned out all these examples can be solved with the same kind of deep learning architecture, which is one that we'll cover towards the end of the class. All right, with that, I'll wrap up. Basically, in the next lecture, we'll learn the first step that we'll always need for all these different models, which is to learn how to represent words as vectors. All right, thanks.